Okay, so how can 6 liters a minute going into a device turn into roughly 24 liters a minute coming out the other side? That's not a typo, then that's not magic. But by the end of this video, you're going to be able to explain exactly what that extra gas comes from and exactly how to calculate it yourself. Let's start with the device that makes this possible, the air entrainment mask. You also hear people call this a Venturi mask, and that name is common in practice, but is not quite accurate. This device uses a jet, not a true classical Venturi tube. A true Venturi tube relies on very specific taper shape to pull in air. This device is simpler than that. Oxygen is forced through a small nozzle at a high velocity, and that high velocity jet pulls room air in through openings called entrainment ports right around the nozzle. That oxygen and room air mix together in a mixing chamber before it ever reaches a patient. So going forward, we're going to call it what it actually is, a air entrainment mask. Now, here's where the size of the air entrainment port really matters. And this is worth slowing down for. If you open up the entrainment port by making it larger, that the window is more larger, more room air gets pulled in around that oxygen jet. More room air means more total gas moving toward the patient, but it also means that oxygen gets diluted more. So FiO2 comes out lower. That's your low FiO2 setting. More entrained air, more total flow, lower oxygen concentration. Now shrink that port down, and that gives you less room air getting pulled in, less dilution. So FiO2 climbs higher, but less air means less total gas moving. So total flow drops. That's your high FiO2 setting, less entrained air, less total flow, higher oxygen concentration. So if you notice that trade-off, turning the FiO2 up doesn't just change the oxygen percentage, it also changes how much total gas the device is putting out. Higher FiO2 settings generally mean lower total flow. Now, that's the device working exactly as it's designed to. But what happens if something blocks the entrainment port or if there's resistance downstream? Say the tubing is kinked or an obstruction the patient is breathing against. Less air gets entrained, just like a smaller port setting, so the source mixture becomes more oxygen rich. But total flow also drops. And if that drop is severe enough, the device may no longer be able to keep up with the patient's inspiratory demand. Then that's how much air they're actually pulling in within each breath. When that happens, the patient starts pulling in extra uncontrolled room air around the mask itself. And now you got a second kind of dilution happening that the device was never designed to control. The result is a delivered FiO2 that's variable and unpredictable, not the clean fixed number that you originally calculated. Now let's get to the math of this. And I want to slow down here because if you understand what each piece of this formula means, the arithmetic becomes easier. And if you don't, it just becomes symbols. Before we touch any formula, here's a practical idea underneath it. One part of oxygen plus several parts of room air is what creates both your final oxygen concentration and your total flow at the same time from that same mixture. Change how much air joins that one part of oxygen, and you change both numbers at once. The formula just tells you exactly how much air that needs to be. So here's the exact formula for the air to oxygen ratio. Air to oxygen ratio equals 100 minus the desired oxygen percentage minus 21. Okay, so let's break down every piece before we touch a calculator. The 100 represents pure 100% oxygen. That's your reference point. 21 represents the room air because room air is about 21% oxygen. That's your other reference point. Your desired O2 percentage, that's the FiO2 you're actually trying to deliver to this specific patient. So this formula is really just measuring the distance between your target and pure oxygen. compared to the distance between your target and room air. That ratio tells you how many parts of room air you need for every one part of pure oxygen to land exactly on your target. And that's the next piece. Oxygen is always expressed as one part. Whatever number you calculate on top, that's how many parts of air go with that one part of oxygen. So let's run it once. Say your target is 40%. 100 minus 40 is 60. 40 minus 21 is 19. 60 then divided by 19 is about 3.1. So for every one part oxygen, you need roughly 3 parts of room air. Written as a ratio, that's about 3 to 1. All right. So now in real clinical practice, you're now always going to sit down to run division every time. Egan's textbook gives you a set of approximate ratios for the FiO2 you'll use the most. But that can be hard to remember for an exam. And that's why we have that ratio. However, here's your table, and 24% is about 25 to 1, which 25 plus 1 gives you that 26 total parts. 28% is about 10 to 1, and 30% is 8 to 1. 35% is roughly 5 to 1. 40% is 3 to 1, and 50% is 1.7 to 1. And then 60% is 1 to 1. And notice that pattern. As the FiO2 climbs higher, the ratio keeps shrinking. That means less and less air per part of oxygen, which matches exactly what we just talked about. Now, one important distinction here, these are estimates rounded for quick use. The exact formula we just worked through gives you the precise number. If you need a fast bedside estimate, this table is what Egan's gives you. Is just though it's an approximate, not the exact figure. So the last piece here, total parts. Once you have the ratio and add the air parts and the one part of oxygen together. For 40%, that's 3 parts air plus 1 part oxygen, which gives you a total part of 4. So you're just adding the air and oxygen numbers together and you get your total parts. And the total parts is what we need for the next step. Now, here's where this starts to explain our opening question, how 6 liters becomes 24 liters out. The formula is total flow equals oxygen input times total ratio parts. Let's slow down on what those words actually mean. Oxygen input flow is the number you dial in on the flow meter. That's pure oxygen going into the device, not the mixture leaving out. Total ratio parts is the number we just calculated, air parts plus the one oxygen part. So you take the oxygen you're feeding in and you multiply by how many total parts make up their mixture. That tells you the total volume of gas, oxygen plus entrained room air actually reaching the patient. This is a piece students often mix up. The number on your flow meter is only oxygen. It's not the total flow the patient is breathing. The device is adding room air on top of that. And this formula tells you how much. Let's put all of this together with an example we opened with. You've got an air entrainment mask set at 40% with an oxygen input flow of 6 liters per minute set by your flow meter. So step one, you're going to find your ratio. At 40%, that's approximately 3 to 1. Step two, we're going to find our total parts, and we just add 3 plus 1, and that gives us 4 total parts. That's our air oxygen ratio added together. Step three, we're going to now multiply. The total flow equals your oxygen input. 6 liters per minute times your total parts, which was 4. 6 times 4 is 24. So this mask is putting out roughly 24 liters per minute total. About 18 liters of that is entrained room air, and 6 liters is the oxygen you dialed in. That's your answer to the question we opened with. The extra flow isn't coming from nowhere. It's room air pulled in by the oxygen jet. And the formula tells you exactly how much. So now one more thing to notice before we close this out. If you increase the oxygen input flow through the same adapter, say from 6 liters to 8 liters, total flow goes up, right, along with it, but the FiO2 you selected stays roughly the same. Because the ratio itself hasn't changed, you're just pushing more of the same mixture. So here's the question for you to sit with. If selected FiO2 goes up, does total flow automatically go up too? Or could it actually go down? Based on everything we just covered, higher FiO2 settings generally mean a smaller ratio of air to oxygen, which means less total flow, not more total flow. FiO2 and total flow do not move in the same direction. And that raises the real clinical question you'll be working through in this class. Once you've calculated the mass total flow, is that flow actually enough to meet the patient's inspiratory demand? We're not solving that today, but that's exactly what you'll work through together in class. But now you have the tools to do the math once you get there.